In this video, we'll go through problem solving based on the application. And the tool that we will take you through today is the block diagram. Now, a block diagram is a specialized flowchart, I would say, where it depicts different components in your systems pictorially, and that way you have an input. So let's have an example of A, B, and C, and your output is in C, and you have an input in A. So a block diagram just basically gives you the ability to figure out how each feature, based on i.e. each of these A, B, or C components, interact with one another to achieve this result. Now, using that, you're able to then further separate it down into its subcomponents, and in that way you're approaching the problem or the application in a top-down approach. So let's look at an example. So with this example, we have a race car that is sort of racing around the track, and then you have two sensors over here which detect when an object is between the two respective sensors. So in that sense, the sensor output, as you can see over here in the electrical signal that it puts out, is like such. So it will be low until an object is detected in between the two sensors. So in our example of the car around the racetrack, it would be evident that the sensor will go high when the car passes through that sensor itself and that part of the lap. So let's do a quick example. So let's say we want to record the lap number for that specific car and then display it on your 7-segment displays. So since we're dealing with sort of a top-down approach and looking at the problem solving skills itself, we won't go through the individual components. So we're just assuming that we have something that is there to display whatever we want to display on the 7-segment displays. Now, a feature of this example is you need some sort of counter to start counting the lap numbers. So then you would have a block for the counter itself. Now, in this case, it's pretty evident that the result of the counter should be displayed on the SSDs. So then that's a simple connection to make. Now, what we want in this very simple example is basically you have your sensor input, so SI. So that would then evidently feed into the counter, right? So depending on the results of that sensor, that would increment the counter as it needs to go. Now, a common way to store a bit of information is a D-type flip-flop, so that's a DFF. And flip-flop has a input for the next state, output for the current state, and then this edge-triggered clock input. Then you have reset at the bottom as well. Now, with your counter, it seems intuitive that it would be made up of multiple D-type flip-flops, and therefore we can just use this single DFF as a representative of all the D-type flip-flops that you have inside this counter. Right. Okay, so let's have a look. We want to record the lap number. So we have our sensor input here somewhere, so whatever pin that's coming out from. And also note that we have a clock in our system. Right, let's say that's running at 100 Hertz, for example. Then you have your counter. So we're working with the D-type flip-flops inside the counter itself. Again, this single DFF is representative of all of the flip-flops within this counter block diagram itself. So it's almost as if it's a sort of section of that we're using in this example. So the next state of your counter should logically be dealt with by another logical circuit. So whether that be combinational, whether that be sequential, there should be another combinational sequence or another combinational block which deals with that. Specifically, I want to have a look at the triggering of the flip-flop itself. So we want it to be a counter, so we can, an easy way that we can see is actually, hey, why don't we just connect the clock to the counter, right? That should work, right? We're expecting then the counter to update or increment every time the car passes through. But does that happen in reality? So if we trace our way through what the inputs of that system would be, so in this case, our clock input is actually this, and this is not to scale, obviously. Notice how that in this sequence we have multiple rising edge waveforms from our clock input. And remember that D-type flip-flops are updated or triggered based on rising edge inputs. So using this specific connection that we have, we can actually say that that's not going to work because it means our counter will update at 100 Hertz instead of when the car passes through to indicate the lap number. So now we know this connection over here is actually incorrect. So a crucial part of this problem solving skills is to actually simulate in your mind what would happen when you connect specific components together, right? So in our example just then, we connected the clock straight to the D-type flip-flops, and we realized, hey, that's not going to work. We're going to update our lap counter at 100 Hertz rather than when the car passes through it. Now, we notice that in the sensor output, when the object is detected up here, over here, we notice that there is one rising edge in that signal input. So we can actually use this because this is exactly what our application requires. Our application requires us to record the lap number that the car is at. The sensor detects when the car passes through that sensor, indicating a lap has occurred. So then it would make more sense to connect this system or this sensor input into your D-type flip-flops. So in this case, it might seem very trivial in terms of which components you should be connected to what, but let's look at another example, shall we? So using the same premise, our example 2, we're trying to, how about this, record the lap time. So contrasting exercise 1 where we're recording the lap number, in this case we want to record the lap time. The architecture remains the same, right? So you still have your SSDs over here, you have your counter, you have your sensor input, and you also have your clock. So this is your 100 Hertz clock that you have, and somehow they have to sort of work together. And again, since there are different ways to implement these counters, we're going to use a representative way of doing it, which is just a D flip-flop to indicate this. So we have Q, that's D, that's your clock trigger. Okay, again, the next state should update based on its current state, and that should be dealt with by another block, and we won't go into that block, which is some form of combinational logic circuit or some form of sequential logic circuit, depending on your application. In our case, it's a simple combinational logic circuit. Now, we're more interested in this input, which is what should we connect to the clock input of your D-type flip-flop. Now, we have our sensor input and we have our clock. Right, so since we want to record the lap time, and it just so happens that our clock is running at 100 Hertz, great, if we have a 4-digit SSD, we can basically count from 0000 all the way to 99.99 seconds, right? Because it's running at 100 Hertz, which means each increment of your counter is 10 milliseconds or 1/100th of a second. So it kind of makes sense. In this case, we're trying to count up the time, so it makes sense that we're just connecting the clock into it. So then let's predict our output. Right? This is an important part of this process, which is you make a decision. So let's connect the clock to the trigger for the D-type flip-flop. Now this is the part where you need to predict what you want it to happen. So in our case, we want to actually record the lap time when the car starts its lap and then stops its lap, and then compare the output to what the input is, to our expected output is. So our expected output can be split into, our expected output is actually just the time for each lap. But notice how in this specific circuit, this clock will continue to run at 100 Hertz, regardless of whether the car has passed the sensor or not. So the output for this counter is actually just going to count from 0000 to 9999 without a care of what the sensor tells us. So it will start counting as soon as the power is switched on, rather than waiting until the car has started the lap itself. Now, for this, we need to then look sort of in a more holistic picture, right? So we have our car running around the circuit, my terribly drawn car, and then we have our two sensors over here. Now, a lap would then can be determined by that sensor over here, right? So the sensor input that we have, the waveform would look roughly something like this, right? So this would indicate that the car is there. Similarly, the second rising edge, the second sort of high waveform also indicates that the car has passed through that sensor. Now, logically, we can say between here and here, that is our lap time. Right? Logically, we can make that guess, or educated guess. And also notice that we have two rising edge triggers in our sensor input, and they can be used to tell us when the lap started and when the lap ends. Right, so that's the start and that's the end of our lap. So then we only really want the input to be running at 100 Hertz during this segment. So if we go back to our DFF, so this means that the clock input has to be changed, right? So whatever clock input we have, we need something to record when the lap has started and record when the lap has stopped. And notice how we have rising edges. So since we know what D-type flip-flops do, we can actually just put another DFF into this input, right? And then that could be fed using the sensor input. And that way we can use this to indicate the start of the lap and the end of the lap. And since we want it to be a start and the end, we can treat this as such, right? So this is that DFF output. So we call it DFF2 output. We want it to go high when it starts, and we want it to go low when it ends. And this can just be reversing by itself. I mean, a simple way that we already know is actually just this, right? So it will just invert its current state when it gets triggered. And then those two triggers to invert those states are based on the start and the end of that car lap. Now that we have this, we need to then look into other logic gates that we can use to connect our clock into. In our case, we want the signal to remain low, so our input, so our output that we want, or our output of this system, of this specific wire, should be low until the lap starts, and then start counting with the clock, and then stop counting once. So then we have our car start and car end. Now, there should be some logic gate here to be able to achieve this